Welcome to the Data Hall YouTube channel. In this video, we are going to talk about how do we identify and treat outliers in R. So outliers are the data points that are different from the rest of the values. And if we leave them untreated, they would create biasness in our results. So what we need to do is we need to identify outliers and then we need to treat these outliers. So we are going to talk about the identification of outliers first, and within identification we are going to discuss three methods, that is identifying outliers using Zscore, IQR method, and then box plot method. So let's start with the Zscore. So what we do is we create a Zscore of the data points, and then we look into the values that are 3 standard deviations greater than greater values, right? So those would be considered as an outlier. So let's first load the data. We are going to use the empty cars data. This data contains different cars, their mileage, their cylinders, etc. But what we are interested in is the carburetors, the number of carburetors each car would have. So if we sort this data, we can have the cars that have 1 carburetor, 2 carburetor, etc. But if we scroll down, we have a car that have 8 carburetors, right? Now this obviously is an outlier, right? It is quite a different value from the rest of the values. So it does seem to be an outlier, but from our test perspective, from our the perspective of the measures that we are going to use, is this an outlier or not? This is what we are going to look in this section. So first we have to calculate the Z-score. For that we are going to use the scale and then we are going to input the empty carburetors column and calculate the Z-score based on the carb column. So this would calculate the Z-scores. These are the Z-scores. What we are going to next do is take because the Z-scores have negative and positive values, we are going to take the absolute values of these Z-scores, right? And then we are going to see if any value is greater than 3 standard deviations, right? If any value is greater than 3, so we get a vector that contains whether a value is greater than or less than 3. We get all these false. That means these values are not greater than 3. But then there is one value at row 31 that is greater than 3, and that's why we have true over here. If we put that into perspective and create a vector that would contain this value, let's output this vector and we can see that this is a row 31. Let's go back to the empty cars data, scroll down, and because we have 32 rows, so this obviously is the second last row. We can see this 8 is an outlier, right? It is different from the rest of the values. Okay, so this was the Z-score method using which we identified the outlier. Let's move to the second method, which is interquartile range method. But before that, let's clear our environment and let's reload the data. This is the same data, but I've just reloaded it so that we have lesser clutter in our environment. So interquartile range is the first quartile and the third quartile, the range between the first and the third quartile. So what we do is we calculate the lower threshold and the upper threshold, and the lower threshold is 1.5 times the interquartile range, and the upper threshold is again 1.5 times the interquartile range. So first we are going to define the multiplier that is going to be 1.5. Let's create an empty vector that would contain these values, and then we are going to calculate this lower bound and upper bound values for the carb column. So we create quantiles. This is the lower quantile, the first quantile, right? So we use quantile function, and 0.25 means it is the first quantile. So we get the value for the first quantile, which is 2, minus the IQR multiple that we have just created into the interquartile range of this variable. If we do that, we get a lower bound. So lower bound turn out to be the number -1. Then we are going to do that same for the upper boundary. And next we are going to look into which specific values are lower than the lower bound. Again, those would be outliers. We do not have any value that is lower than, remember, we had an outlier at a higher value. So this specific part of the code would turn this value 31, the row 31, to be an outlier. And if we execute this whole code, we identify the outlier, and it says that it is the value that is at row 31. So that was the interquartile range method to identify outlier. Let's look at one more method that is more of a visualization method, and that is box plot. So what we do is we use the box plot function, input the empty cast data, and first let's create box plot for each of the variables in our data. So what we are going to do is we are going to have a box plot horizontally, right? So these variables would be horizontal, our box plot will be vertical, and their fill color would be light blue, right? These are optional. I've just defined them so that our box plot looks somewhat nicer. This is the box plot that we would have. Now you can see we have MPG, and there are certain variables that are not appearing over here. If I can drag it, then those would become visible. Now all the circles that we can see over here, these are the outliers, right? So we have outliers in each of these variables, right? But not in MPG. We do not have an outlier in cylinders. We have this outlier in carburetor, right? Now we could have drawn this box plot for a single variable. In this case, we have drawn this box plot for all the variables, but let's look at a more deeper look at the carburetor variable by just plotting this box plot just for the carb variable. So we again use the box plot function, but now instead of having the whole data set, we have a specific column. We define the heading of that box plot. So in this case, we would have a title of this box plot, and then what title would we have for the x-axis, the color, the border, and whether we want it horizontally or not. And previously we defined it horizontally. So variables were at the x-axis, but now we want the variable to be on the y-axis. So if I execute this code, we get the box plot just for the carburetor variable, and we can see that this is our outlier at the value 8. So that was related to identifying outliers. Let's move to how do we treat outliers. So we mainly have 3 methods. There are other methods, but these are widely used methods. We can either trim the outlier value, that is, this is the outlier. We can simply remove this value. We can winsorize it, that is, replace this value with the nearest non-outlier value, or take the log of all these values. So then we wouldn't have any outlier. So let's start with trimming. And for that, we are going to load this robust base package. Now, first you need to install this package. I have already installed it, so I'm not going to install it. But if you want to install it, then you would use install.packages and specify the name of this this package, right? So I'm not going to execute this install packages command. I'm just going to load this library, and let me clear this environment, and next load the data again. So I'm going to define a threshold after which the number of values that I want, to the percentage of values I want to trim. So I have defined 0.1, that is 10%. So I want to trim the 10% of the lower and the higher values. This is the threshold that I have defined. Then it is important that we sort the variable. So I'm going to create a new vector that would be a sorted carburetor values. So if I can show you this variable, we have these values sorted. And next I'm going to take the length of this sorted variable, that are 32 observations, and multiply it with the percentage so that we can have the number of observations that we want to trim. Now we get 3.2, that means we need to drop 3.2 observations from the starting and ending of the data. But obviously 3.2 doesn't make any sense, so we round this value and that rounds to 3. Let's save this into this vector number of trims. And now what we are going to do is we are going to trim those values using this this command. So we get a new vector that is trimmed carburetor, and you can compare this vector with the one we just got. Now previously we had more values. So in trimmed carburetor we have 26 values. In the original sorted carburetors we had 32 values. So there is a gap of 6 values that had been dropped, because we identified that we would drop 3 values from the lower side of the series and 3 values from the higher side of the series. So you can see that those higher values and the lower values had been dropped. Now in this case it isn't quite visible because we had lot of ones, and it would just drop these 3 values. So we again have these ones, but these are not outliers anyways. Let's move to the second method, which is winsorization. So in trimming, it would drop those values, right? It would drop the top 3 and the lower 3 values. But in winsorization, rather than dropping them, it would replace it with the nearest non-outlier values. So let's clear our environment first, and let me load the data again. So I'm going to define the lower and the upper threshold. In this case, I want to have the lower 5 percentile and the higher 95th percentile. So I want to create the lowest 95th percentile and the highest 95th percentile. And that I'm going to do is using the quartile function. So I have this lower value, right? And I have this upper value. The upper value is 4.9. So what this means is that replace all the values, all the lower 5% values with 1, and replace all the higher 5% values with 4.9. So instead of dropping them, we are going to replace them. And for that, we are going to use the parallel min and parallel max functions. So I'm going to execute this. I just created a new data frame that is called empty cars winsorized. This is exactly the same data frame, but I just do not want to change my original data frame. Let's execute this command and let's look at the empty cars data. Let me sort this. You can see we have all these ones over here, and the outlier was 8, and then we had a value of 6 that had been removed with that had been replaced with 4.9, which is the non-outlier value. Okay, that was related to outlier. The last technique that we have on our list is transforming the data points, that is taking the log of these data points. But let me clear my environment, load the data again, and we just take the log of empty cars carb data and create a new variable. Let's call it carb log. And now if I can show you this variable doesn't contain any outlier. So there aren't any values that are quite high or quite low values, right? So that was working with outliers, how to identify and treat outliers. So I hope this video was useful. Do subscribe to this channel, do hit the bell icon, and thanks for watching this video.